Hey everybody, I hope you all had a good week. I'm going to pick up where I left off with this Lenovo X1 Carbon Gen3. So just in case you're watching this new, the situation is this. We have the laptop, it's not powering on when the button is pressed. We have verified that there's 20 volts on the main power rail. I've also injected 20 volts on the main power rail just in case there was any issue with that. Still not powering on. I've verified that the power button has 3.3 volts and it is working. It's dropping to zero when pressed. We have compared the diode mode readings on the inductors with a working laptop, and when we compared those we found that inductor L3, which is the switched 5 volt power, is reading low. It's reading 0.034 when on the working laptop it's reading 0.270. So let's pick it up from there. And just to show which inductor is L3, so L3 is this inductor right here. So on this faulty laptop, in diode mode, at L3 we are measuring 0.034 volts. On a working laptop at L3 I am measuring 0.250 volts. So it seems like this is way too low. So let's try and troubleshoot and see if we can find out what's wrong with it. The first thing I decided to do was to inject 5 volts onto that rail and see if anything would heat up. Now the resistance I actually measured in resistance mode on this inductor was 37 ohms, so it's no way an absolute short, but I thought it might be a good first step to see if I connected my own 5 volts onto that rail would anything heat up and identify itself as the component that has the low resistance. So introducing my multimeter, sorry, not my multimeter, my power supply, connecting my black wire to ground and my red wire to that inductor. I set it to 5 volts because we saw last week that is the 5 volt rail. So this is inductor L3 and this is the 5 volts here. And when I powered it on, it drew 110 milliamps. So that was not enough for anything to get hot. I left that running for a couple of minutes. It kept drawing 110 milliamps, but nothing was heating up. So in this scenario, voltage injection is not going to be any use. Obviously, because it's a 5 volt rail, I can't increase this anymore in order to, draw more current and heat up whatever component has the low resistance. So we need to move on to something else. Voltage injection is not going to help us solve this problem. Back to our schematic, we have our TPS 51220 IC here. Now we have already identified that SW1 is the one that connects to inductor L3. L3 is where we're measuring the low resistance, and after L3 this is referred to as VCC5M_out. Now this is the switched 5 volt output from this IC. So we need to find out, where does this go? I temporarily removed inductor L3 and I verified that the low resistance value and the low diode mode reading are on this side of the circuit. So what I decided to do next was to search through our schematic and find all instances of VCC5M_out and see what circuits this is supplying power to. Okay, I've searched around the schematic for all instances of VCC5M_out, and this actually powers quite a few different circuits on this board. So any one of those circuits could be the cause of our low resistance, but just let's take a look at where it goes. So first of all, it goes to U2, which is one of the ICs on the board. So you can see here VCC5M_out comes in. I've drawn in that arrow just to indicate the direction. So this VCC5M_out powers this IC by the looks of it, because it comes into a V in UVLO under voltage lockout, I think that is. So that's one path that it takes. The next path that it takes is onto this IC U16, which seems to be responsible for CPU core voltage here. So it's the input here, it goes through two inductors and onto U16, so that's another path that it takes. Another path that it takes is providing power to U28 IC. You can see VCC5M_out comes down here through an inductor and onto this IC. And it also provides power for U32. So once again we have VCC5M_out, and that is providing power to U32 right here. I've pulled all these together in Photoshop and sort of crudely drawn in the path that our 5 volts takes down to each of these circuits. But it gives you an impression of what's going on, right? So we have our 5 volts power generated from this IC right here, and then it is fed down to other secondary circuits where it supplies power to each of these ICs. Now what we do know is that in diode mode, with the power switched off obviously, we measure 0.034. So it's likely that one of these circuits is the cause of our low diode mode reading. So wouldn't it be nice here if we could somehow disconnect each of these one by one and check and see which one of these is causing the 0.034 volt diode mode reading? Now on some of the boards that we've seen, there is a special pad where there's just a blob of solder that connects two parts of the circuit, and if you want to isolate a part of the circuit, you just remove that blob of solder and you can test the two parts of the circuit independently. However, that's not the case here. I don't have any means of disconnecting them easily. However, if I look at this first circuit here, I can see that if I remove this resistor here, I can disconnect this part of the circuit from this part of the circuit. Not as convenient as moving a solder blob, but at least we do have a means of doing it. On the second path that it takes down to U16, we have our 5 volts coming in here, and it comes through 3 series inductors here. So if we wanted to disconnect this part of the circuit temporarily, we would have to remove these 3 inductors. But it is feasible. These are quite big inductors, so we could actually do that. For this part of the circuit, our 5 volts comes in here through FL52 and onto our ICU28. So to isolate this part of the circuit, we could just remove FL52. The last one down here, which is U32, if we wanted to isolate this part of the circuit, we could just remove FL53. And that's where I'm going to start. So to isolate this part of the circuit for testing, we just need to remove FL53. I've located FL53 and U32 on the motherboard. So this is where our 5 volts comes in. This is the input voltage for U32, and then the output is here on L7, which corresponds to L7 right here. So what we need to do first is to remove this. So with my hot air station, I heated up this component here and just removed it. So I didn't take it off the board completely, I just moved it across like this and soldered it onto this pad. So that breaks the circuit here. And if you look at how that is on our circuit diagram here, that is essentially the removal of this component. So we've now isolated the part of the circuit with U32 and the part of the circuit where our 5 volts is generated. So what I wanted to do now is take the same diode mode reading on this side of the circuit and this side of the circuit and see which one has the low diode mode reading. So introducing my multimeter in diode mode, I place my red probe to ground and my black probe to this point right here where we've removed the inductor. So that is equivalent to this point right here on our schematic. And when I place it there, what I find is I get a diode mode reading of 0.034. Next, I want to take the diode mode reading for the other side of the circuit. So I place my black probe to this pad right here, which is the equivalent of measuring at this position. And when I measured there, I found that the diode mode reading was 0.276. So what do those readings tell us? Well, what those readings tell us is that our 0.034 volt diode reading is associated with this part of the circuit here. When we cut this part of the circuit off from our main 5 volt rail, our 5 volt rail measures 0.276 volts, which is comparable to our working laptop. So our fault seems to be isolated to this part of the circuit. The question then, of course, is which of these components is responsible for that low diode mode reading? Now, it could be any of these components on the input section to this IC here. It could be one of these capacitors, it could be possibly this resistor, or it could be the IC itself. I decided to remove these 3 capacitors first. So through the magic of Photoshop, I can just remove those 1, 2, and 3. And when I did that, I took a diode mode reading again, and when I did that, I found that it had the same diode mode reading. So it's nothing to do with the capacitors. I sort of knew that anyway, because when capacitors fail, they usually fail completely, and I would expect a much lower diode mode reading if the fault was caused by a failed capacitor. So once again, with my hot air station, I put a bit of flux on the IC and I carefully removed it, just like that. So with that IC now removed, we need to check our diode mode reading again. So once again, red probe to ground, multimeter in diode mode. I'm placing my black probe to that same position again. We now read OL. So what does that tell me? Well, that tells me that our 0.034 volt diode mode reading was through the IC itself. So it seems like there is a problem with that IC that we've just removed. I checked online and it is actually possible to get these ICs pretty easily actually from AliExpress and from other sources. This is the one here, VT387BF. So what I'm going to do is I'm going to order one of these, and when it comes in we'll try and fit it. Now if I was braver I would temporarily take this from my working Lenovo X1 Carbon Gen3, but I just don't think it's worth the risk. I haven't done one of these before, so I don't want to break two laptops. I can order this, I'll get it in and see if we can get this working again. That's my video for this week, guys. I tried a few new things in this video. I'm always interested in what you think of them, like where I tried to join the schematics of the different circuits together. Did it work? You can let me know down below. Any comments are welcome, positive or negative, I don't mind. I'll be back with something else next week, and I'll talk to you then.